organizers for having me in this seminar series. I think it's a great opportunity, and I'm very glad to be giving this talk. And so I'll be talking about some recent work with Benjamin Withers that came out last June in this archive number on the existence of this arbitrarily long-lived linear perturbations to black holes. So I'll begin with some motivation for the work, as well as presenting the main result. Then I will move on to introducing the tools and techniques used throughout, among which we use this hyperboloidal slicing of all the spacetimes we consider. After that, I will present a simple analytical example that demonstrates the main result of the work. And then I will move on to constructing what we call these optimal perturbations, how to construct them and what they are. And finally, just end with some conclusions and future directions. Okay, so eigenvalues are one of the most successful tools of applied mathematics. Among their many applications, I can name computing the spectra of observables in quantum mechanics, solving partial differential equations, studying resonances among many different physical systems. However, in most of these cases where eigenvalues offer the correct description at all times, let's say, the systems under consideration are governed by what is called a normal operator. What I will be talking about and what we'll see is that when the systems are governed by what is called a non-normal operator, eigenvalues fail to capture the dominant effects in the dynamics of time-dependent systems, at least at intermediate times. So this already raises the question of what is a normal operator. So let me just go through the definition. A normal operator A in a Hilbert space is defined by having a complete orthonormal set of eigenfunctions with respect to the inner product in the Hilbert space. This is the same as to say it is unitarily diagonalizable. And another equivalent definition is that it commutes with its adjoint, where the adjoint is defined as usual, given here, where now the inner product again is a 1 in our Hilbert space. And so the important point here is that the operators that we're mostly used to are the self-adjoint Hermitian operators, where the operator is equal to its adjoint. And these are a special case of normal operators, but all self-adjoint operators are normal operators, but not all normal operators are self-adjoint. And the topic of this talk will be about non-normal operators. So it is important to have this distinction in mind, namely that you could have a non-self-adjoint operator that is still normal. And so to illustrate why eigenvalues in these non-normal systems fail at intermediate times, we need to go through this historical example that is the Ort-Sommerfeld operator in hydrodynamics. This operator comes basically from the linearization of Navier-Stokes equations around a flow of this type called plane pusted flow. So this is a two-dimensional flow where it has a parabolic mean velocity profile of this kind, and it is incompressible and viscous, and it has the so-called no-slip boundary conditions at these walls, which means that both the velocity field and its set derivative are 0 in both of these points. So these are 4 boundary conditions for a fourth-order operator coming from the linearization of Navier-Stokes. And the important point about this type of this operator in this flow is that it is non-normal with respect to an inner product defined from the energy of these perturbations, these linear perturbations on top of the flow. So since this type of flow is also interesting for real-life experiments because it resembles the flows you would have in real-life pipes, it was widely studied, and the first eigenvalue analysis of this operator showed that it actually shows an unstable mode at a critical Reynolds number of this value. This basically is to say that there is an eigenfrequency in the complex plane that moves into the unstable half of the complex plane. However, in real-life experiments of these types of flows, they wanted to attribute this instability, this dynamical instability, to a transition from a laminar type of flow to a turbulent flow. However, in real-life experiments, precisely this transition from laminar to turbulence happened at much lower values of Reynolds number. So there was this tension between what the spectrum of the operator told you and what real-life experiments were showing. And it was not until a non-model study was performed, where here I should open a parenthesis, and by model, during the whole talk, I will be referring to behavior dictated by eigenvalues alone, so by the spectrum of the operator. So when a non-model study was performed, it revealed that these linear perturbations on top of this flow actually exhibit transient growth in their energy in a time domain. So let me show you how this works with an example. So here on the left, I have plotted for Reynolds numbers below the critical value. So this is all a stable regime. I have plotted the block curve, which is basically the maximum possible energy of these linear perturbations at each moment in time. So this is over all possible initial configurations of the perturbation. And the red dash, which is an actual energy of a linear perturbation, and is what we call an optimal perturbation, because it is constructed such that it maximizes its energy at a target time, where in this case, I have chosen this target time to be 18. So there are two very distinct parts of this plot. There is a transient regime, so at intermediate times, we see that this is all normalized to 1 at time equals 0, by the way. And we see that in this intermediate regime, transient regime, the energy of the perturbation actually grows. That is allowed by the black curve that denotes maximum possible energy. It can grow, and it does in this optimal perturbation. And then we have a model regime, which is at symptotically late times. The energy of the perturbation does decay as per dictated by the longest lived mode of the operator. So in this case, remember, we are in the stable regime. So all the eigenvalues are exponentially decaying. So this transient growth shows that this is not captured by the eigenvalues, because precisely they are all exponential, decaying exponentials. And we can still have these non-model effects that come in this form of the energy of the perturbation growing. And so this was a much better motivation to relate this to the onset of turbulence at low Reynolds numbers in the actual flows. So it's also interesting to understand or to see what the initial configuration of this type of optimal perturbations that grow looks like. And schematically, so in this type of diagram, they saw that these optimal perturbations have these streamwise vortices in their initial configuration. So this is time equals 0 along the direction of the flow. And these are precisely the components of the initial data that get amplified by the linear dynamics and lead to this growth. Again, this is all at linear level. It should be emphasized. So now, why do we care about this? Well, the point of the talk is that the Hamiltonian governing linear black hole perturbation theory is also non-normal with respect to a choice of inner product. And it has already been shown to have consequences, important consequences on the spectral stability of quasinormal frequencies. So in this paper by Jaramillo, Macedo, and Schick, where they initiated the study of the spectral stability of black holes using pseudospectrum techniques. And as you probably know, this is related to the distance that the eigenvalues move in the complex plane under an additional perturbation to the radial operator that governs quasinormal modes in these black holes. In this talk, however, I will not be dealing with the spectral stability of quasinormal frequencies due to non-normality. I will be talking about the time domain, and there have also been some previous discussions on these non-modal transient effects in gravitational systems, namely these two papers, and more concretely, in this paper, Jaramillo wants to associate the transient effects with the transition from the in spiral to the late ring down of a binary black hole merger in a first approximation given by linear gravitational perturbations to a Schwarzschild black hole. And he finds that there cannot be, through arguments based on pseudospectrum quantities, he finds that there cannot be transient growth, at least in this setup, in the energy of this linear perturbations. So what we do in this work is we generally ask the question of what is the maximum response that can be developed in linear black hole perturbations. And in doing so, we initiate a systematic non-modal analysis of black hole systems, gravitational systems. And what we find as the answer to this question, so is basically that there exists, due to coming from the non-normality of the operator, there exists this arbitrarily long-lived sums of decaying quasi-normal modes. So these arbitrarily long-lived linear perturbations of black holes. And just as well, to show the main result here, on the left, I have the analogous plot as in the hydrodynamic case, but now for gravitational perturbations of the Schwarzschild black hole, where again, the black curve denotes the maximum possible energy of these perturbations at each moment in time over all the initial theta configurations. And the red dash is one of these optimal perturbations that is targeted at a time of 8.5 here. And so in this case, from the maximum energy curve, so the black curve, we can see that there cannot be energy growth because this is normalized to 1 at 0, and it doesn't go above 1. So it is bounded above by 1. However, there are still interesting transient effects that come from this non-normality. And in this case, they are realized as this period of time, this transient period of time where the energy of the perturbation, so now the red dash, is actually non-decaying until the time chosen to maximize its energy. So basically, the only thing that it can do to have maximum possible energy at this time is to track this plateau, this constant plateau. And then after it has reached this maximum energy, it will decay according to in this case, the pair of fundamental quasi-normal modes of the Schwarzschild black hole for gravitational perturbations. And so on the right, to understand again what these optimal perturbations look like, I'm plotting here the energy density of this optimal perturbation in red dash, the same one, in the conformal diagram of the Schwarzschild black hole, where I'm also showing these white dash slices are the constant time slices, so they're hyperboloidal slices. So each of these constant time slices corresponds to a value of tau here on the left. And this is the first initial time slice. And so we can see that the initial data in this case for these optimal perturbations in Schwarzschild correspond to some localized energy packet at the horizon, and also less dominantly, but also at future null infinity, that as time evolves, travels along the horizon without actually falling into a black hole or escaping to future null infinity, so without losing its energy, until this red dot time, which in the conformal diagram corresponds to this very, very small white dash slice at the very end. So now let me go through how to actually get here. So for that, in general, we are considering massive complex scalar perturbations, so governed by the Klein-Gordon equation, on top of static fixed static backgrounds of this form, where I will not be talking about all of these, but in our work we consider the static patch of the sitter, Schwarzschild ADS black brains, all of these two in any dimensions, and all. So in all of this, we use these hyperboloidal slices that come from this change of coordinates from these Schwarzschild-like coordinates by these functions h set and r set. R set basically gives you a compactification of the radial coordinate in the region of the spacetime that you are interested in for the perturbations. And h set gives you this bending of the slices that makes them to pierce the future event horizon in all of them, and also future null infinity in the Schwarzschild black hole. So these two functions are actually dependent on the spacetime under consideration. But the common feature for now these coordinates is that Z is a the compact radial coordinate between 0 and 1, where 0 corresponds, I will be talking about the sitter later on, but 0 corresponds in the sitter to the north pole of the sitter. So it's this word line here, this vertical line in the conformal diagram, to the conformal boundary, this time-like boundary in ADS, and to future null infinity in Schwarzschild. Whereas Z equals 1 corresponds to the location of the future event horizon in all of these. So why do we use these slices? Well, first of all, the shape of these slices makes them a natural choice to track the amount of energy that is leaving the region to actually study a lifetime of linear perturbations. But also in this slicing, after performing a decomposition of the full scalar field in orthogonal eigenfunctions in the transverse d minus 1 direction. So this is, I will be working in d plus 1 dimensions. So after performing this decomposition in orthogonal eigenfunctions in these transverse directions, according to the symmetries of the spacetime. So for Schwarzschild and de Sitter, this would be spherical harmonics, and for Schwarzschild ADS black branes would be plane waves. And then doing what is called a first order time reduction. So now our fundamental fields will be this vector of the scalar field and its first time derivative. We can get the Klein-Gordon equation of motion for our perturbation in this Schrodinger, time-dependent Schrodinger form, where now the Hamiltonian H, is a 2x2 matrix of differential operators. So in these slices, the regular eigenfunctions of H correspond to the quasi-normals in each spacetime. And so we will be labeling these quasi-normals with a single index n, ordered by the distance to the real axis of their corresponding quasi-normal frequencies omega n. Okay, so now since we want to study this maximum possible response of linear perturbations, the natural observable to look at is the energy of these linear perturbations on a constant time slice. So this is basically given by this integral of the energy current, so the stress unit tensor of the scalar field contracted with the time-like Killing vector of all the spacetimes. And this energy current contracted with the future-directed unit normal to the slices. This gives us the energy over a constant time slice of the perturbation. And so from this energy, we're going to define an inner product such that the energy of a perturbation C can be thought of as the square of the norm in this inner product. And right away from the definition of the energy and using the local conservation law of the energy current, we can compute the outgoing energy flux, which is we define to be minus the time derivative of the energy. And so in both de Sitter and Schwarzschild ADS, we find that this reduces to a boundary term at the future event horizon of this form. Whereas in Schwarzschild, there is also the analogous term at future null infinity where energy can also escape. But the important point about these fluxes is that, as you can see, they can only be either 0 or positive. So this is already telling us what Jaramillo found, that there cannot be transient energy growth in these linear perturbations, this linear scalar perturbation. And now the key feature of this talk and this work is that the Hamiltonian that I just showed in the last slide, in the Schrodinger type form of the equation of motion, is actually non-normal with respect to this inner product coming from the energy of the perturbations. And as per the definition I showed at the very beginning of what a normal operator is, this means that there will generally be overlaps between different modes in this inner product. And so a first direct consequence of this is that, say we construct a linear perturbations built from the sum of the first m quasi-normal modes with this coefficient Cn, so their exponential time dependence with their frequencies and their radial dependence. And now we want to compute its energy. Well, because of these overlaps, its energy is not simply going to be the sum of each individual energy of each mode, but it's going to have these cross terms appearing, which are actually the ones that open the possibility for, say, more or interesting transient dynamics happening at intermediate times that are not dictated by the quasi-normal frequencies. You see, if we didn't have these cross terms, basically the maximum response would be saying, okay, we set all the coefficients of the overtones to 0, and we only keep the fundamental mode, and this will give us the slowest decay of energy. Okay, so
May I
just to
ask
see,
question?
yeah, I don't know if we ask questions, but yes, sure.
I'm just the quasi-normal mode of what? The black hole? Or the
yes. So Yes, let me
But you are
go.
considering a massive Clay-Gordon
Yes.
field on this, no?
Yes, these are massive. So
Okay.
yeah, I'm talking in generality here, but what we consider are actually massive, complex, massive
Okay,
scalar perturbations
okay. But
on.
the perturbation, I mean, but when you're talking about quasi-normal modes, these are modes of the black background, no? I mean, quasi-normal modes of the
Yes, exactly.
geometry.
This equation is on this fixed black backgrounds. Yeah. So there are perturbations to the background.
Okay.
Yes.
Yeah, carry on.
At linear order. Okay.
I have another question while we're at it. How do you handle the mass term in Schwarzschild at future null infinity?
How you handle the mass term?
Because
what do you mean with mass?
There are no massive fields near future null infinity. So if you do compactification in the Schwarzschild case and you have a mass term in your Klein-Gordon equation, that tends to be singular. Do you see that? Do you see a problem there when you do the transformation for the Klein-Gordon equation with the mass term?
So you mean that you will have a singularity of the equation at future null infinity?
Yes, that is
We have
not.
a formal singularity only. I mean,
with the mass term, it's not formal, right? With the mass term, as long as the M doesn't vanish, that's actual singularity.
well, actually, the mass term is somehow restricting the field that it has to, decay sufficiently fast. We investigated a much simpler problem years ago with Euler-Fodor, and we had young Miss Higgs such that the Higgs was massless, but the young Miss field was massive, and we were puzzled for long. And then we also considered on flat Minkowski background the Clay-Gordon, massive Clay-Gordon, and of course you can integrate by a green function, and you can really get something that you have a sort of self-similarly expanding oscillations with oscillations in time growing without upper bound. And you are getting closer and closer to scribe with these oscillations, and the energy is reserved. But you can get safe smooth scribe in that setup. Even in numerical experiments, we had this trouble, so we could explain. But I'm puzzled now. How can you avoid this?
Yes. So basically, we take Schwarzschild massive scalar perturbations in the Schwarzschild background, and we're going to compute the spectrum of the Hamiltonian numerically in the end. And so what we're going to do is just take the parts of the spectrum that correspond to this. So not the parts of the spectrum that give you the branch cut in the imaginary axis, but only the point. So the point modes reflected by the imaginary axis. So only exponentially decay modes. But I will be talking about this later on, or how we pick a subset of modes and construct the perturbations from that subset.
Okay.
I don't know. Okay. Okay. So yeah. So we were looking at the energy of sum of modes, and this is not going to be simply the sum of the energies of each mode, but it's going to have these cross terms that come from the non-normality of the Hamiltonian, and thus non-orthogonality of its eigenfunctions, the Quasinormal modes on this inner product. And so to see what consequences this can have, let me go through this analytical example, simple analytical example, which is going to be in the static patch of the sitter. So the sitter is the maximally symmetric solution to Einstein gravity with a positive cosmological constant. And in a set of coordinates called global coordinates that cover the whole manifold, we have that the constant global time slices, which correspond to horizontal slices in this conformal diagram, are so again in D+1 for the sitter are d-dimensional hyperspheres, such that the endpoints, so here and here, are the north pole and south pole of the spheres. So they are actual points in space-time, and these vertical lines are not conformal boundaries as they will be in Schwarzschild in ADS, sorry, but they are the origin of coordinates. Sorry, they are world lines of the spacetime. So we're going to work in the sitter because, in this case, because of its main symmetries, Quasinormals are fully analytical. The radial dependence are just given by hypergeometric functions. And so consider, for instance, fixing D to be 3 and this choice of the mass, and L is just the angular momentum quantum number. And now say we construct a linear perturbation for, again, these are scalar perturbations with the first two modes. So these are actually very simple. They don't even have a radial dependence. And now we compute its energy as I showed earlier. And we find that, as we expected, we find that there's this cross term that comes from the non-orthogonality of the modes in the energy inner product. And thus it comes from the non-normality of the Hamiltonian. And this cross term opens the possibility of setting a slower decay than that set by the fundamental mode, which would be this exponential decay. So a better way to see this is just by expanding the energy around t equals 0 in a Taylor expansion, which is here on the right. And we can see that firstly, the sign has to be negative because we already concluded that there cannot be energy growth. But secondly, this combination of the coefficients in a perturbation makes it possible to make a choice such that we kill the first order in tau, which is simply A1 minus 2A2. And this is also killing the next order in tau, actually. But the point is that by killing these orders in tau around t equals 0, we already have a parallel decay that is lower than any exponential decay that could be set by these Quasinormal modes. So we can do this algorithmically and generalize for a sum of the first M Quasinormal modes, again, for these choices of parameters and for scalar perturbations. And surprisingly, this has a closed form expression, and we can actually compute the closed form expression of the energy in terms of the number of modes in our sum. So again, these are ordered modes from the distance to the real axis. And then simply we have chosen the coefficients in this algorithmically in this way to kill as many coefficients in the Taylor expansion as we can. And by using M modes in the sum, we can kill the first two M minus 2 orders in tau. And so we can actually take the limit when M goes to infinity of this closed form expression for the energy, and it's just 1 at all moments in time. But I'm going to emphasize that we should always consider a finite sum of modes, so M finite, because in this infinite limit, the gradient of the scalar, the gradient of the perturbation, actually diverges at the horizon. So this cannot be regarded as a physical perturbation anymore. But we can keep studying this simple example and compute its outgoing flux. And we see that it basically remains 0 for this transient period of time until it has a very sharp peak at this log M time. And so this is the time when the energy is starting to either fall into the black hole or escape to future null infinity. And so we can regard this as the lifetime of the perturbation. Now, the important point about this example is that simply by increasing the number of modes, so M in our sum, we can make this lifetime be as arbitrary long as we want, but again, never infinitely long. Okay, so now let me talk about these optimal perturbations, because the first question that I said in the motivation was we wanted to study the maximum possible response to these linear perturbations. So this simple analytical example is already demonstrating that there are arbitrarily long-lived perturbations, but they don't necessarily have to be the most optimal. So in order to study this slowest energy decay, we can simply say, oh, let's just maximize the energy at each moment in time. So at target time tau star. And parentheses here, here we basically used parallel techniques to the Orson-Sommerfeld case in hydrodynamics. More specifically, in this paper by Reddy, Schmidt, and Henningson, they computed these optimal perturbations for the Orson-Sommerfeld case. And so a systematic way to do this maximization of energy at each moment in time is through this so-called energy growth curve, where again, this term energy growth, is inherited from the hydrodynamic literature, but we do not have growth in these cases. And so this is this G of tau, which is by definition the maximum energy at each moment in time in tau over all possible initial data configurations. And so simply by saying that our perturbation at time tau can be formally written as the time evolution operator acting on the initial data, we arrive to this form of this energy growth curve that is by definition the norm of this time evolution operator with the Hamiltonian age squared in this energy inner product. So in other words, by computing this squared of the energy norm of this time evolution operator, we have at each moment in time, so evaluating at tau, we have the maximum energy that that any linear perturbation can have at that time. So a first set of bounds on G of tau comes straightforwardly from firstly the fact that there is no transient growth. This is one as bounded by one above, and then from the fact that there exists the fundamental mode. So G of tau has to be bounded between these two for each moment in time. But in reality, in order to be able to compute things, we need to restrict to a subspace of M quasinormal modes. So we call this subspace W. So this will be a subspace of solutions built from the first M quasinormal modes. And then we find an orthogonal basis to the subspace via the Gram-Schmidt orthogonalization procedure. And we will call this Cn, which again are orthonormal in this energy inner product by construction. So now we have two bases in which we can expand perturbations restricted to the subspace, so sums of the first M quasinormal modes. And we will be calling the coefficients in the quasinormal basis C's and in the orthonormal basis D's. And now one can prove that the energy growth curve projected onto this subspace, so this norm of the time evolution operator, but the Hamiltonian is not projected onto W, this is an exact equality, can be written as the 2 norm, so the usual Euclidean 2 norm of this M by M, now it's an M by M matrix squared, where HW is this M by M matrix constructed from UW, which comes from, it's just a change of basis matrix from Gram-Schmidt, and DW, which is the diagonal matrix that has a spectrum on its diagonal. So this non-calligraphic HW can be thought of as a Hamiltonian projected onto W in the orthogonal, in the representation of the orthogonal basis. So now we have arrived at something that we actually know how to compute, which is the 2 norm of a matrix. And I will be reviewing this now in a second. But furthermore, not only can we compute the 2 norm of this matrix, which gives us the maximum energy of any linear perturbation in this subspace W at the time tau, but we can also extract the initial data of a perturbation that reaches the maximum possible energy at the target time tau. So I will be now reviewing how to do these things. Also, I forgot to mention this. Now, since this is the energy growth curve for a subspace of solutions, there's this sharper bound on the full energy growth curve, where this leftmost inequality comes provided that in W we always consider the fundamental mode. So now what is the Euclidean L2 norm of a matrix? Well, this is simply the maximization of the matrix, of the norm of the matrix acting on a vector of the vector space, normalized by that vector. And this can be proven to be the maximum eigenvalue, the square root of the maximum eigenvalue of this A star times A, where star is will always be, during this talk, the conjugate transpose. And again, this last equality is simply the maximum singular value of the matrix A, which can also be proven from the left here. So we can compute then simply this maximum eigenvalue of this combination for this matrix here, or also the maximum singular value in what is called the singular value decomposition of the matrix. So let me go through what this is. The singular value decomposition of any matrix, even rectangular M by M matrix, is B. It's simply the factorization of this matrix into a unitary matrix U, a rectangular diagonal matrix sigma, and another unitary matrix V, where the columns in U are called the right singular vectors, and they're eigenvectors of B times B star. And similarly, the columns in V are called, the columns in U are left singular vectors, and the columns in V are right singular vectors, and they're eigenvectors of B star times B. And the entries in the diagonal of this rectangular matrix are the singular values of B, and they are the square root of the eigenvalues of both B star times B and B times B star. So simply by using unitarity, we can express this factorization in this way, and then choosing the entries that correspond to the maximum singular value in the diagonal entries of sigma, we can get to this form, this equation here, which is basically telling us that the maximum response of B is elicited by this vector Vmax, which is the right singular vector corresponding to the maximum singular value. And this is usually called the right principal singular vector. And we know this is the maximum response because I haven't proven this, but one can prove that this maximum singular value is actually the norm of the matrix, the true norm of the matrix. So now translating this back into the black hole case, we have that we can extract initial data of the optimal perturbations in W that maximize their energy at a target time tau star via the singular value decomposition of this now M by M matrix that is basically the representation of the time evolution operator projected onto W in this orthogonal basis that we constructed. And so the vector of coefficients for the initial data that reaches this maximum energy at this target time tau star is simply the right principal singular vector in the singular value decomposition of this matrix. So in order to not get lost in these details, let me just summarize where we're right now. So the question was, what is the slowest possible energy decay of linear perturbations? To do this, one can just maximize the energy at each moment in time, and this has this name energy growth curve from the hydrodynamic literature. That is simply the true norm in the energy inner product of the time evolution operator, but we do not know how to compute this, so we need to restrict to a subspace W spanned by the first M Quasinormal mode. And so in this case, this is basically the Hamiltonian projected onto W. This will give us this projected energy growth curve. And now to actually compute these quantities, we need to find an orthogonal basis for W with Gram-Schmidt, which are these psi n functions. And in this orthogonal basis, this G of W of tau now is simply the square of the true norm of a matrix, which is something we know how to compute. So this will give us the maximum possible energy at time tau star for any linear perturbation in W. And through its singular value decomposition, we can extract initial data that constructs these optimal perturbations that maximize their energy at the target time tau star. Okay, so let me just now show the numerical examples for the Schwarzschild black hole. So we'll be considering the standard treatment of perturbations through the Rebecca-Wheeler-Cyril equations. using the same form of the energy inner product. This is closely following the paper by Jaramillo, Macedo, and Schick, where they use this to compute the superspectrum in the Schwarzschild black hole. And in this case, the Quasinormal modes are not analytical, so we'll have to resort to numerics, which will simply be Chebyshev's spectral methods, discretizing the radial set coordinate. So this means that the Hamiltonian will be now a matrix where n+1 is the number of points in the grid. We also have to discretize the energy norm into a weighted 2 norm with current matrix T. And just to mention, an efficient way of performing the Brown-Schmidt in these numerical examples is using this QR decomposition. So now let me show the results for gravitational perturbations. So spin 2 or L equals 2 in the Schwarzschild black hole. Here is the main result. We have 3 different growth curves for 3 different subspaces of solutions. So they have 3 different dimensions. First, we have the subspace of the 10 first modes, the subspace of 19 and 39. And we can see, as I spoiled in the beginning, this has this no-model transient regime where it has a constant plateau. And then after this plateau ends, it decays as predicted by the fundamental pair of Quasinormal modes. So what we can see from just the black curves, ignore the red for the moment, is that by increasing the number of modes, we have that this transient duration is increased in a logarithmically scale with m, with the number of modes or the dimension of w. And now taking the subspace of 39 modes, we construct this optimal perturbation that has target time 8.5, so reaches the maximum possible energy at this time. And so in order to reach this maximum energy at this time, it has to track this plateau for the duration of the plateau, and then decay according to, again, the fundamental modes. So it has this transient period where its energy is not decaying. And this is purely a no-modal effect that is not captured by the eigenvalues. Whereas in the asymptotically late times, the eigenvalues, so the energy is dictated by the eigenvalues. So just to see how this perturbation looks like in the conformal diagram, here on the left, we're plotting the absolute value of the scalar field, and on the right, the energy density of this perturbation. And well, you can see that it is basically a localized energy packet at the future event horizon that starts propagating along the horizon without falling into a black hole, and then at this target time, this white slice that corresponds to this red dot, it starts leaving this region, the energy, and so the perturbation starts dying. And so the main point is that simply by yes.
So is it like, so the intuition will be, if you want to keep the energy in the outer domain of dependence, you want to have almost purely outgoing initial data near the horizon and almost purely incoming initial data near future null infinity, right? Is that what comes out of this procedure?
Well, so you can think about it that way, but so it's important to remark that these perturbations are constructed from ingoing modes. So all the modes are ingoing into the black hole and outgoing to future null infinity. So it's not that we're choosing outgoing modes.
Not outgoing modes, but so I think that's a different terminology. But you know, let's say I'm thinking in terms of time domain evolution, and you can then construct your initial data such that it's primarily outgoing, right? It has only characteristics that are pointing to the right, if you will.
Yes.
And they are still constructed from ingoing modes in that sense, if you do a frequency domain decomposition. But your initial data, you know, you can build a time derivative, and then you can construct its derivative along the outgoing characteristics. So that's the sense in which I'm saying that, okay, it should be purely outgoing so that it doesn't fall into the black hole right away, and vice versa on the other side. So this is
Yes,
kind of intuitively what I would do if I were to do that in time domain, right? Is that kind of what you get from the frequency domain analysis? That's what I'm wondering. Is it the same thing or related?
so yes, exactly. You can think that these have this outgoing behavior from the initial data and through this transient period of time, and then they start.
You can probably show that formally, right? You can do the characteristic derivatives in those two directions, and then you can formally show the components of your initial data that you've constructed, how it's related, I'm guessing.
Yeah, okay. We haven't done that, but yeah, that's a good point. Yeah.
Okay.
To make it
Thanks.
more intuitive, yes. Thank you for the suggestion.
Actually, if you even you prepare the initial data in the time domain such that it's outgoing parallel to the horizon, the field is scattering on the geometry, and then there should be part which is going into the black hole region. So I'm really puzzled what sort of boundary conditions you used here at the horizon. So
Yes, exactly. So the boundary conditions are infalling to the horizon and outgoing to fictional infinity. And these are basically in these hyperboloidal slices, these are reached via regularity of your solutions at both these points because of the shape of these slices. So this infalling and outgoing boundary conditions are encoded into the regularity. So this is, I think I don't know if I said this, but this is one of the main reasons we use these slices.
And it's also not that
if you have a massive
sorry.
field on a even on Minkowski background, the massive field has to decay faster than any polynomial order towards scribe. So why, I don't know why do you talk about outgoing boundary condition at scribe? I mean, the field itself, the field equation tells the field to decay such that it's not going to reach ever scribe.
So maybe I'm wrong, but I think these are the standard boundary conditions for Quasinormal modes. So the sorry.
If I just a clarification that if you're using the same foliation that was used in the paper by Aramillo and others, that only works for massless perturbations, right? So for studying perturbations in static de Sitter patch, it's all right because that's the Poiseuille-Taylor problem, and that does correspond to a massive field propagating in de Sitter background. But when you're talking about black holes, the foliation works only for massless perturbations. I think Rodrigo can clarify this if I'm not too wrong.
Yes, right. But these are massless. These are gravitational perturbations. So maybe this was a bit confusing, but we're basically using the regular Wheeler-Serril equations, and in these plots here, these are gravitational perturbations. So these are not massive scalar perturbations, let's say. In this case.
Yes, so that sounds right because for static de Sitter, it's fine. Those can be interpreted as massive field propagating, but when you use this foliation for Schwarzschild or for any black hole, it's massless. I don't think this foliations work for massive scalar fields in Schwarzschild or Schwarzschild.
Right. Yeah. Yes. These are not massive.
Yeah, that was also the question from Neil again. I mean, it's quite difficult to get the mass. But I think also from what Esteban was saying, I mean, it makes sense here. I mean, that it's not that the perturbation stays forever. I mean, it can maximize the duration of this plateau, right? But then there are scatterings in the potential. There are everything that goes around, and eventually things will be absorbed by the black hole and everything. So the conditions are here. Everything's consistent.
Yeah. The perturbation surely it cannot stay forever. It always has an ultimate decay via the Quasinormal mode rates. And again, sorry for the confusion, but these in the Schwarzschild case, we're only doing these gravitational perturbations to the regular Wheeler-Cerilli equation. So they are not massive scalar perturbations.
No, I think it's coming from the approach you use. You have a finite series of quasi-normal modes. Just think about if you have a massive Clay-Gordon field on Minkowski spacetime, there is no radiation going out from the spacetime. So even if you use hyperboloidal slices, the total energy on these slices are constant. And when you see the evolution of the field, of the massive field, of course there is a decay of the amplitude. But because you have to have the energy conserved, this means that the frequency is growing without upper bound. So if you cut your series, you lose, the rest of the history, which means that the approach is what you presented is usable only up to a limited evolution time, and then it's not capable to represent the field, the history of the field anymore with this finite number of modes.
But for the massless case,
there has to be an infinite or unbounded increase of the frequency to preserve the energy, because the amplitude is decaying.
But here is the massless case.
Yeah,
So
it's
here
massive field is this. I mean, in the simplest case, it need not to be Schwarzschild. It happens already in Minkowski.
But these are different setups, right? One setup is massive massive in Minkowski. That's what you're describing. And the other setup is massless in Schwarzschild. I mean, these are different setups. Here there is no conservation of energy.
This is massive field, no? Or...
No, this is
no,
mass.
it's not.
That's what we're
No mass, no mass. This is just Ridge-Wheeler.
Okay, I understand. Thanks.
Yeah, sorry for the confusion. I should have clarified that at the beginning when I was showing the tools. But in Schwarzschild, it's these plots are always for massless, in this case, gravitational situations. Okay, any other question? Okay, so just to see what the initial data of this optimal perturbation. So this is the same red dash perturbation shown here. We plot this so the absolute value of the coefficients in both the Quasinormal basis and the orthonormal basis for this subspace of 39 modes. And we can see that in the orthonormal basis, they are all of the same order 1, more or less. There's nothing really remarkable about their values. Whereas in the Quasinormal basis, they take these very, very large orders of magnitude. And this is already telling us that for the energy to remain constant for this transient period of time, there need to be very, very large and precise cancellations between the different non-orthogonal modes. And so this is also a way to see how at intermediate times, these the Quasinormal modes do not do a good job of capturing the time domain dynamics, because all the cancellations are coming from this very large orders of magnitude of the coefficients, not the actual modes, which are just exponentially decaying. So this is just a nice picture to see this. And now let me just summarize. So the main result of the talk was that there exist arbitrary long-lived sums of decaying Quasinormal modes. These mathematically are possible due to the non-normality of the operator that covariance these Quasinormal modes, which leads to the non-orthogonality of these modes in an inner product defined from the energy of the perturbations. And physically, generally, these are possible because of the existence of the event horizon, where the perturbation can localize and its energy can propagate along for this transient amount of time. Also, I would like to emphasize that these lifetimes are arbitrarily large by including more and more modes, but never infinite. So there is always this ultimate decay of the perturbation via the longest lived Quasinormal mode. And here I've only talked about the static patch, an analytical example, non-optimal analytical example in the static patch of the sitter, and these numerical optimal examples in flat Schwarzschild. But in the paper, we also discuss optimal examples in the static patch of the sitter, where everything is fully analytical, and optimal examples in Schwarzschild areas, black brains, where it is numerical, but also analytical example in the BT-set black hole. And obviously the flat Schwarzschild that I presented here. So we find the same results for all these spacetimes. So we find some kind of universality, and it is interesting to see if this would have some observable consequences in the domains where horizons play a role. So astrophysics, analog black holes, or condensed matter systems through ADS-CFT. And now from this last plot that I just showed, the question of fine-tuning very naturally rises. This is because we saw that the coefficients in the initial data of these optimal perturbations in the Quasinormal basis take these very, very large orders of magnitude that have these very precise cancellations. But this is not a simple thing to answer whether or not these are simply fine-tuned perturbations, because Quasinormals do not form a complete basis of solutions, so of linear perturbations. So one could think that there could be other linear perturbations that are not constructed by sums of Quasinormal modes that could also exhibit some similar behavior. But nonetheless, it is a very valid question that we would like to explore further. And also another natural next step would be including back reaction, either perturbatively or in a fully nonlinear simulation, to see if we can find the imprint of these linear perturbations in this setup. Okay, so that's everything I have to say. Thank you very much for your attention, and please ask more questions if you have.
Thank you.